we'll go it again, see what we can think. All right, Dalton's law of partial pressures. Hang on, let me check this again. Yep. Okay. So here we go. So we'll go over this again to make sure that we're all in good shape here. In this case, the only variable is pressure. So temperature is held constant. The number of moles is held constant. The volume is held constant. Okay? And so all we're going to be doing is adding things together. And notice that when we do that, you'll be able to add the individual pressures together to get the total. One thing is the pressure has to be in the same units. The total pressure is simply the sum of the partial pressure. Here's a good example of this. I have my little container here that's at 5 liters and 20 degrees. 5 liters and 20 degrees, 5 liters and 20 degrees. I'm going to add 0.6 moles that has a pressure of 2.9 to 1.5 moles that has a pressure of 7.2. The moles are the same, so the pressure is going to increase. So it's going to be 2.9 plus 7.2 is 10.1. So if this first one is 2, and this is 1, and this is 3, and it's important to note that these can't be reactant. They can't react to each other. This answer is going to be what? 6. Yeah, it really is that simple. The percent of gases in the air. So we can do a percent composition if you want. This is our percentage of the gases, like what would be in this room. And I would simply multiply the percentages times the total, and I could get the individual partial pressures. I can go the other direction and add up the partial pressures, and that gets the total pressure. Again, we talked about this a bit last time. And we did these problems last time as well. So we can go over that. So someone asked in another class, why is the answer 0.3 here? Anyone? Sig figs. And what sig figs in particular? What step made it to be 0.3? Yeah. The what? Yeah, right here. When I did this subtraction, remember addition and subtraction use digits after decimal. This has the fewest digits after the decimal, which is 1. Therefore, my final answer is only allowed 1 digit after the decimal. All right, we did these. We did this one? Okay. And there's the answer real quick. All right, we're going to skip here. We're going to play a video. If you're watching this online, watch the Professor Dave video that is listed. All right, hopefully that was helpful. And now we're going to talk about today, we're going to move on to talk about Boyle's law, Charles' law, and Gay-Lussac's law. And you need to add, because apparently this got left out, we're going to do the combined gas laws. So you are going to have a little bit of freehand writing today. All right, first of all, let's make sure we all can see and understand units. So you should have this table in there. 750 milliliters, what am I measuring? Volume, right? This is milliliters is a unit of volume. And that's going to be V. 35 degrees Celsius is measuring what? Temperature, and that variable is what? That's a T, right? So I want you all to do the rest of them. Good. Any questions on these? You got them? Okay. Boyle's law is named for Charles Boyle, who studied the relationship between pressure and volume. What he discovered was that they had an inverse relationship. That is, that at the same amount of gas, at the same temperature, if I increase the pressure, I decrease the volume. And you can imagine this if you had a balloon that you squeezed, right? If I increase the pressure, I can decrease the volume. We've all done this. Okay? Inverse relationship. You're going to have to know these, so we're going to ask you like the name and the law. So one way to think about this is you can know that you boil your peas and vegetables. Boil your peas and vegetables. That's how you remember boil is pressure and volume. Boil is pressure and volume. Okay, so you're going to need to, you got to do something to keep these, because we're going to ask you, like I said, questions about the scientists, and this is one of these we ask you about. Okay? The temperature is held constant, and in other words, the amount of gas is also held constant. Pressure increases, volume decreases. Pressure decreases, volume increases. And this is the formula you're going to need to write down. P1 V1 equals P2 V2. Okay? It's just PTV, but. Y'all good? You have that formula written down.
It's already on our
Let's visualize this again. I gave you the balloon illustration, but hopefully this will work too. Notice I'm leaving the temperature the same. I'm leaving the amount of gas the same, but I'm increasing the pressure. The volume's decreasing. And it's directly proportional. It turns out if I double the pressure, I reduce the volume by half. And when the volume doubles, the pressure decreases by half. All right, so any of y'all used a bicycle pump? Maybe back when you were kids, you has a little cylinder and you push down. What's going on there is I'm increasing the pressure, I'm decreasing the volume, I'm increasing the pressure, and at the point that I have more pressure in the pump than there is in the tire, air moves from the pump into the tire. So here's a situation at 1 atmosphere of pressure, I can have 60 milliliters, and if I double that pressure to 2, I have 30. I double that again to 4, I have 15. I double that again to 8, and I would have 7.5. Every time I double the pressure, I half the volume. It's a nice direct relationship there. So let's go ahead and practice one. To compress nitrogen at 1 atmosphere from 750 milliliters to 500, what must the new pressure be? I'm going to recommend when you're doing tests, and I'm going to tell you this for your homework and for your tests, as you read a word problem, figure out what formula you're going to use and write the formula down, and then fill it in. In this case, I know I'm working on Boyle's law, and I have the formula here. So let's identify the variables. This is going to be P1. This is V1. This is V2. And I'm looking for P2. What I want to see on all your homework is the formula with the variables put into it. So with the units, this is 1 ATM. And 750 milliliters equals P2 and 500 milliliters. Can you use your outstanding algebra skills and solve this? Okay. You have to write this. It doesn't count if I don't see at least that. You can write the next one, if you wanted to, which is what you notice here, if I do this and I've done it right, I notice that I'm going to cancel out the milliliter units, and the only units I'm left with are what? ATM. Is ATM an appropriate unit for pressure? Yes, that means I did my algebra right. Okay? You don't have to write this step. I mean, I recommend it. It takes you an extra second. I do want to see this step with all my units, because that tells me you read the problem right. Okay? This tells me you did the algebra right. And whenever we get to next year and we're doing AP Chem, you're going to want to write this for particularly your FRQ answers to show people what you're doing. My recommendation is you write the formula, fill the formula in from the word problem, solve it so you can see your own work. Okay? I want to see those units written. All right, you guys handle this one, and then we'll work it together. So what variable is this one? V1, and this is P1, and this is V2, and I'm trying to solve for V2. So I'm going to plug in 1 atmosphere, 1.56 liters, okay, And so 3.00 atmospheres and P2. Okay? And so I solve that, and ATMs cancel out, and so P2 equals what? Hopefully everybody else got that right. 0.52 liters. Fantastic. What's that? What'd you get?
Divide 1.56 by 3.
Yeah, so in this case I'm going to divide, we're just doing algebra here. 3.00 ATM. And then 3.00. Okay. So that leaves me with 1.56 divided by 3. You did. This is a pressure of 1 ATM, and this is a pressure of 3. So I divided the pressures here. Let's try another one to make sure we're all working with Boyle. See if we can get Boyle's law here. So 4.31 is what? V1, and 0.755 is, okay, and 1.25 is P2, and so I'm trying to find V2. So 4.31 liters, 0.755 ATM equals 1.25 ATM and V2. All right. Can y'all solve that? So V2 should be equals what? So 4.31 times 0.755 divided by 1.25. You got what again? 2.6. Yeah, okay. That's good enough. Is that what everybody in here got?
Yeah.
You got over there? Okay, cool. All right. That takes care of Boyle. Now let's talk about Charles. Let's talk about Charles. So Charles, and a way to remember Charles' law, I don't know if some of y'all have these little bitty satellite dishes up on your roof. There's a company that used to do that called DirecTV. So we say that Charles watches DirecTV. Charles watches DirecTV. That helps you remember that Charles understood the direct relationship between temperature and volume. Temperature and volume. And if I heat up a certain amount of gas under constant pressure, the volume will increase. There's a direct relationship between temperature and volume. So you can remember that Charles watches DirecTV. Yeah, he was a balloonist. And I don't know if any of y'all have ever, how many of y'all ever seen hot air balloons? Even in the air. So have any of y'all ever seen them when they're getting set up? Yeah, it's a pretty cool experience, right? They start up with this flat thing. They blow air into it with just fans. It's the same air that's on the ground, regular air, and then they start heating it. And that causes it to expand. It's the same air. It's not helium. It's not magical air. It's just, it is in this long distance one, but in the original balloons and the ones like at the Albuquerque festivals, they're just heating the regular air, and that causes the air to expand. And because it expands, the same mass of air has a larger volume. Because it has a larger volume, what happens to its density? It becomes less dense. And that means the colder, more dense air that's around it falls down and lifts it up. Okay? So that balloon rises. Okay? This is why the balloons were important. In this case, pressure is held constant. So in this case, since I've got an opening here, the pressure on the outside is the same as the inside, so we're going to keep that, but we're going to have a collection of air here that's less dense around it and less dense inside the balloon. So here's my formula. V1 over T1 equals V2 over T2. It's a direct relationship between temperature and volume. Charles watches direct TV. Good? And y'all can see this little animation. The masses staying the same, pressure staying the same, but as I heat it, to keep the pressure the same, I have to expand the volume. Okay? Temperature increases, volume increases. Temperature decreases, volume decreases. A direct relationship. Yep. Good. Y'all all matchy-matchy today. That's so interesting. So notice whenever we're at 0 Kelvin, does the volume ever actually get to 0? Why not? Because why? Yeah, a volume of 0 means there's utterly nothing there, but if I've got a collection of gas molecules, the molecules themselves do take up space. When we do our little math here, we pretend it doesn't, right? But I do know, for instance, if I have these little carbon dioxide molecules that I cool down, or I keep cooling them down, at a certain point when they cease being gas, then this stuff doesn't apply. So yeah, just be aware of that. All right, here we go. Volume can be measured as a liquid or gas, liters or milliliters. I could be solid, centimeters cubed. It doesn't matter as long as they're the same on both sides. Temperature, however, must always be in Kelvin. And year after year in this chemistry class, in AP chemistry class, in every chemistry class we teach, we have students that make this mistake. They jump in and do their math in Celsius. Don't do that. Your math needs to be done in Kelvin. Probably told you that last class. I'm going to tell it to you again over and over and over. Okay? Temperature must always be in what? Kelvin. And if you start doing math and you notice your temperature is a negative number, you're wrong. Temperature has to be in Kelvin. All right. Let's try this. A sample of neon has a volume of 1.83 liters at 23.5 degrees Celsius. At what temperature would the gas occupy 5 liters? So let's go through this. The 1.83 is what variable? V1. And 23.5 is T1. And 5 liters would be V2, and I'm trying to find T2, right? I'm going to do this both ways because I think it's worth showing you why. I notice that my temperature is in what units? What's it supposed to be in? How do I get it to Kelvin? Add 273. And so if I do that, I'm a little punchy. Let's come over here and we're going to write this. V1, 1.83 liters over 296.5 Kelvin equals 5.00 liters over T2. Okay? Again, I want to see this written. Okay? With all my units. I can do my little algebra rearrangement. And I would note that T2 equals that's right. Is that right? Nope. I don't think so either.
That's not what I did.
That's the other way around.
I did. I think you'll get the same answer. 5 divided by.
I don't think so.
Got that, but I'm multiplying the number that I got by.
What was that?
You'll get the right.
That was right. Yeah.
It's the same answer.
So what'd you do?
I did. So I wrote it out like V1 over T1 equal to V2 over T2.
Uh-huh.
And then like I multiplied V1, I mean T1 by V2. And I got 1482.5. And I divided by 1.83. There you got it.
So that's right. Okay. And what'd you get?
810.11.
Okay, I got the same thing, but I did
Okay.
something different. You just cross. Yeah, y'all cross.
Yeah, that's what I didn't. Okay. Yeah, you end up with the same. You're right. You end up with the same, but that's. I'm gonna do my same brain here. No, it ends up with the same. It was right. Okay.
I was just saying I did it a different.
Cool. All right. So we all got 810, and this seems reasonable because 1.83 and 5. What's that ratio? So 5.00 divided by 1.83 equals 2.73, and 2.73 times 296.5 equals 810.
Yeah, that's right.
Okay? And that works. It's great. Good thing to keep in mind. All right. This is a beautiful thing. It works. Now let me show you. I want you to write this down, but I also want you to write wrong. Okay, because we're going to do it the wrong way. I want to show you how wrong it is. So if I'd said it was 1.83 liters and 23.5 degrees Celsius, V2, somebody said, oh, it'll work out the same. Oh, yeah, let's convert that. Convert that to, how do I convert that back to Celsius? Subtract. Let's subtract 273 from this. What do we get? Okay. We're going to keep that in mind. 537 is what everybody got, yeah? We'll keep this in mind because this is the right answer. Let's go see what happens if we do it wrong. Y'all plug those numbers in and tell me what you get in terms of Celsius. Is that what y'all got? Actually do it because I want you to see that what you're going to get here.
Yeah, I
and you got 64.2 degrees Celsius. There is quite a bit of difference between 537 degrees Celsius and 64.2 degrees Celsius. Right? Okay, don't do this is wrong. I will tell you on the test, in your multiple choice answers, for almost all of the problems, we have worked out a solution where if you do it with Celsius, that answer's there. It exists. Right? So be aware of that, yeah. I just did that because I wanted to show you how to check. You don't, unless I tell you up here in the problem, you wouldn't have to do that. You could leave it in Kelvin. I just do that because I wanted to show you because somebody might say, well, you can just do the math and then convert it, right? And I'm like, no, it like fundamentally is wrong to do the math in Celsius.
How come it doesn't?
Because Celsius is a scale of degrees, and this is an absolute scale. So, yeah, the relationship is based on an absolute relationship, because this is a direct relationship. Because remember, you can go below 0, right? And you can't have negative volumes. All right, cool. Now that we know that, and we're all going to use Kelvin for all of our temperature work in chemistry. This 290, so 443 Kelvin, right? How'd you get 810? Let's plug this in here. It's still off, but let's see. Let me find a calculator here. Let's see what's right or wrong here. So it's 1.83 divided by 296.5. Yeah, that's wrong. Y'all are right. All right, we'll skip this one. Let's try that one. Did you get it? This one. That we got? Is that right? Okay. If I want to, I can rearrange this, right? I reduced the volume. Therefore, to maintain the same pressure, I must also reduce the temperature. So that's one way when you're doing multiple choice problems. Of course, you can just look, right? I can check the ones that are greater, and I can get rid of those. Let's see, nobody's skipping today. So after I do this, I do my punchy. T2 should be what? Okay. And of course with sig figs, it really should be just what? 340. Any questions about Charles' law? Because Charles watches DirecTV. Good? That's fine. It's just when we get all done with sig figs, it'll be 340. Yeah, it should be 341.8 or something. What?
Yeah, I got 341.96.
There you go. Yeah, so it would have been, if you were doing 3 sig figs, you're right. That would be 342. All right, we've got another law to talk about. That is Gay-Lussac. Maybe. I'll unfreeze the computer here. Gay-Lussac's law says that their volume is held constant and there's a relationship between temperature and pressure. And so this is when you're out camping, you don't throw a can of unopened can of beans into the fire because that causes a problem. What might happen? It'll explode, right? And that's because if I'm trying to hold the volume constant and I increase the temperature, the pressure will increase. And it's a direct relationship as well. I don't have a cute little saying for this one, but you can remember the other two, and that will eliminate this one. Pressure, a relationship between pressure and temperature. Somebody said that in a spirit of COVID here, that Gay-Lussac needs toilet paper, and so maybe that works for you, whatever works. Just to understand that there's a relationship between pressure and temperature. Pressure and temperature. And again, you can visualize that by thinking about the cans here, right? And here's some more pictures. There's a direct relationship between pressure and temperature. I increase pressure, I increase temperature. Increased temperature, increased pressure. All right, let's see if we know how to do this. A sample of neon has a pressure of 2.8 atmospheres at 23.5 degrees Celsius. At what temperature will the gas have a pressure of 4.8? Let's identify our variables. 2.8 is P1. 23.5 is T1, but let's go ahead and convert that. That should be what? And 4.8 is P2. And I'm asking you to find T2, right? Let's plug our variables in. Remember, this is what I want to see on your homework. 2.8 ATM with units, yes. 296.5 Kelvin. Okay. 4.8 ATM. And T2. All right. First of all, I did roughly what with the ATM? Almost doubled it. So that means that my temperature is going to need to be almost double. Let's test that theory. Again, I want you to write this down. Feel free to rearrange it if you need to. Right? So again, you could do this. Okay? You can do that, and you can punchy. Type it in your calculator. 508. And so my sig figs looks like 2. So we could do like, 500 or 510. 510 Kelvin. Should be right. Seem reasonable? Okay. Good? Okay. Everybody okay with that one? Do the next one. Everybody got it? Okay. This 470 is what? P1. 77 Kelvin is T1. Let's see. P2 is what we're asking, and 25 degrees Celsius is T2. But what should I do with this? Kelvin, which is going to be what? Kelvin. All right, so P1 is 470 millimeters of mercury. T1 is 77 Kelvin. P2, and that's 298 Kelvin. Now, just looking at the problem, what happened to the temperature? It increased by a lot, right? I mean, more than 4 times, just as a quick estimation, right? That means I'm going to expect what out of my pressure? Yeah, it's going to increase a lot as well. All right, so let's go ahead and we can put this over here. I can rewrite this as P2 just so you can see it. 470 millimeters of mercury times 298 Kelvin over 77 Kelvin. Get rid of the kelvins. We do all our punchy, and pressure 2 equals what? 1800, right? Because we had 2 sig figs here and 2 over there and 2 there as well. Good? All right. Everybody knows how to do Gay-Lussacs, right? Fantastic. We'll skip that one. This is not in your notes. You're going to have to write this down. I don't know how we missed your notes. It's really not hard. Okay? Combined gas law says that the amount of gas is held constant. Basically, we have a sealed container, and then it's a flexible, so I can change the volume and stuff, but the amount of gas is held constant. By combining Charles and Boyle's and Gay-Lussacs, I end up with what's called the combined gas law. This is the one I actually recommend you write down on your sheet. This is P1 over V1 equals P2 over V2 equals P1 over V1. Stop. Let me say this again. P1 times V1 over T1 equals P2 times V2 over T2. Right. See, but now you remember. All right. The nice thing is if you will write this down, if you're reading the problem and it doesn't mention temperature, you cover this up, and whose law do I have? Boyle's law, right? If it doesn't mention pressure, I cover this up, and suddenly I have Charles' law. If it doesn't mention volume, or it says volume is held constant, I cover the volume up, and now I have Gay-Lussac's law. So by having the combined gas law, and the cool thing is you could actually write that like it says something happens at 25 degrees. That's cool. You could write 25 degrees in both places. They cancel out. You get the same answer. But by knowing the combined gas law, you can actually do these kinds of problems. Y'all good? Okay. We're going to practice combined gas laws. Your homework, again, is going to be pages 5 through 9. Right now, I want you to go to your homework, page 8, and we're going to start there, so you guys can get some practice on combined gas law. So your homework, page 8. This says a helium-filled balloon at sea level has a volume of 2.10 liters. That's volume 1. At 0.998 atmospheres, that's P1, and 36 degrees Celsius. I need that in Kelvin. How do I do that? And so that equals 309 Kelvin. That is T1. If it is released and rises to an elevation at which the pressure is 0.900 atm, that's P2, and the temperature is 28 degrees Celsius, it's T2. What will be the new volume? So I'm looking for V2. Okay? And again, y'all can just write the little above your problem so you can keep up with it. So my combined gas law, again, is P1 V1 over T1 equals P2 V2 over T2. So let's take my variables that I have over here and plug them in. So P1 is 0.998 atmospheres. This is what I really want to see. 2.10 liters. Okay, remember I want to see this. This needs to be written down. This will help me know if you are doing your math right, if you're setting the problem up correctly. I need to make sure that you know how to do this, okay? Good. So I can rearrange this problem, right? So this is 0.998 ATM, 2.10 liters, 301 Kelvin, 309 Kelvin, 0.900 ATM. Okay, cancel out ATM and Kelvin. That leaves me with what units? The only units left are liters. Is liters appropriate for volume? Yes. Okay. So now I can do this, and I can do the punchy. What did we end up with? What'd you get? 2.3 liters. Yeah. Well, let's see here. So I started off with 2.1 liters. I reduced the temperature, so that should have reduced it, except I also reduced the pressure, which should have expanded it, and so that ended up with 2.3. Is that what everybody else got? Is that what you got in the back row? You good? You got that too? You're good? So I'm going to, if I'm doing this, I'm multiplying all these guys. Okay? And then I'm dividing. So if I was typing this in the calculator, I might type this whole thing, and then I do divided by 309 times 0.9. Y'all see how combined works? Very good.
As long as you know
Yeah. This is really just about reading the problems and sticking them in the formula. What's that?
about plugging the numbers.
Yeah.
Can you take a look at that? Because I keep getting it.
Let's take a look.
Like I keep getting the same answer, but it's different than that one. I don't know if I just plugged it in.
Oops. What you do here? Yeah, so this, what you're saying is all this then divide by this, then multiply by this. So on the bottom here, I would change that to how you said it was this times this times this divided by that, and then that answer times that.
Oh, okay.
Yep.
All right.
What you got? Yeah. Okay, y'all work the next one. Okay, and then we're going to keep going. I'm going to introduce ideal gas law. What's that?
How can you have 0 degrees Celsius?
What's 0 degrees Celsius? 273 Kelvin. What happens at 0 degrees Celsius? Yeah, water freezes, right? Yep.
What is pressure and volume? Well, pressure and temperature at STP.
At what?
STP.
What is STP?
Standard temperature.
Okay, so what's the pressure? We went over this last class, guys. What's the pressure? You get this, something you're going to have to memorize. Standard temperature and pressure. Pressure is 1 atm. Temperature is 0 degrees Celsius, which is 273 Kelvin. That's something that's got to get stuck in your head. Obviously, you guys this year will have it on your reference sheet. It just needs to be part of your normal process. All right, so 0 degrees Celsius, or what's that in Kelvin? 273 Kelvin is T1, and 1 atm equals P1, and 30.0 milliliters is V1. Temperatures increase to 30 degrees. That means it's going to be what in Kelvin? 303 Kelvin is T2. And the sample is transferred to a 20 milliliter container. That's V2. What will the pressure be? So I'm looking for P2. Okay? So let's plug this in. 1 atm, 30 milliliters, 273 Kelvin equals, let's see, T2 and P2 and 20 milliliters. Okay? Everybody okay with that? Do something wrong? We did all right? Okay? Let's rearrange our formula if you want to. The only units left are what? ATM. Is ATM appropriate for pressure? All right, so now I can do my little punchy. What do we end up with? Equals what?
1
1.2. Is that what you got? No?
I got 1.6.
All right, well, let's do this. Let's do,
Round up to
I
2.
meant to do 1.7.
okay. What'd you get, 1.6?
Yeah.
6. Yeah, since this is, again, this should have been 2, but that's okay.
Actually, it should be 1.7.
Yeah,
It's
because
like
it has
1.66.
1.66.
Yeah.
It would be 1.6.
There we go. All right. Yeah, again, some of these problems weren't written for sig figs because of the one, you're right, the 1 ATM means there's only one sig fig here. 30 times.
Would you prefer us to put 1.7 or would you prefer 2? Or it doesn't matter?
Yeah, you can, I mean, again, if you will write the calculator and then write underneath it, give me the sig figs, I'll be able to see both. Yeah, what? Oh, yeah, so I'd have 3 sig figs, 3. Yeah, all these have 3 sig figs. So actually my answer should have, yeah, those are 3 sig figs. That's 3, and that's 3, and that's 3, and that's 3. My answer should have 3 sig figs. 1.66 or 67? Cool. Yep. Cool. Yeah, everybody got that one? Sweet. We are ready to keep going. Yeah, we're going to go back to the notes. We're going to do a quick intro here into the Did we watch the video today? Dalton's Law today? Did we watch the video today? Okay. Yeah, I thought so. All right. Let's talk about the ideal gas law. Gases are considered to be ideal when at 1 atmosphere of pressure and 273 Kelvin. Particles will take up 22.4 liters. Particles don't have any intermolecular interactions. All right. Okay. This bottom one is really the point here. Ideal gases behave according to the kinetic molecular theory. All right. They're not attracted. They don't repel. We're going to consider they don't take up volume and space, things like that. Okay. All right. The ideal gas law, though, contains all of the variables. So the one thing we haven't talked about with combined is moles, in other words, the amount of gas. We're going to start considering it now. PVnert, or PV, equals nRT. Now, y'all know what P means. That's what? Pressure. And we're typically going to, and to use this law, we have to use units of ATM. Volume. To use this law, we're going to have to use liters. N is going to be what? In what moles, right? R, we're going to talk about in just a second. T is going to be temperature in what units always? Kelvin. Very good. All right. Here we go. Pressure must be in ATM to use this formula. Volume must be in liters. N is the amount of gas in moles. R is what's known as the ideal gas constant. Basically, for gases that are obeying the ideal gas law, it's 0.0821 ATM liters over moles Kelvin. That's the constant. It lets us eliminate basically these variables are here to eliminate the ones that we're not trying to solve for. And I'm going to relax the units rule when it comes to writing R, okay? You don't have to write the units of R every single time. I do need you to be aware of the units of R, and this is going to come into play later on. So if I'm using the ideal gas law, I have to convert my pressure to ATM. I have to convert my volume to liters. I have to convert amount, because if I give you grams, you've got to convert it to moles. Obviously, temperature always has to be in Kelvin, so you're already used to that. So, Pivnert, the ideal gas law. Here's a question. How much nitrogen is required to fill a small room with a volume of 27,000 liters to 0.985 atmospheres at 25 degrees Celsius? So, Pivnert, we should write the formula, PV equals nRT. Because here's the thing, I can talk about that little box in the back of the room being 22.4 liters, but that's only true, that's only going to be true at STP. And this room, thankfully, although it's uncomfortably cold, this room is not at STP. Right? Because the T in STP would be what temperature? 0 degrees Celsius, that would be unpleasant. Right? We experienced that a few weeks ago, right? So the question is how much. So in chemistry, what are we using to measure amount? Moles, right? So this is moles. And so my unit is N. Is required to fill a small room with a volume of 27,000 liters to 0.985 atmospheres at 25 degrees Celsius. All right. 27,000 liters is what variable? V, volume. And that's in the right units already, liters, that's okay. 0.985 atmospheres is what? Pressure. And ATM is the right. 25 degrees Celsius is temperature, but
290.
okay, and that's my temperature. R is a constant. That means it's constant. That means it's 0.0821 all the time. We're doing this math. So let's write it out. So I've got pressure, 0.985 ATM. Volume is 27,123 liters. And that equals N, which we're trying to solve for. Okay? That's not right. I keep doing this. Okay? And what are my units, just for fun? Y'all don't have to write those. What are my units for R?
ATM times liters per mole times Kelvin.
Okay? And 298 Kelvin. What's that?
Do we have to write, like,
What did I say about that?
you said no, but like, in general, not, like, that's not right now, but in general, do we just?
Generally, I want you to write units for most things. These units get kind of complicated. I'm writing it right now for this one, and I'd like you to write it for this one so that we can see how they cancel out to solve for the right one. And so, yeah, so we're just doing this sort of as an example. I know the units of R can be sort of tough to think about. Good? All right. Again, I want you to write this out. This is pretty easy, though, right? Because N's going to be over here. I'm going to divide the whole thing by over here by, and if I do this, ATM, liters, so this cancels, right? Good? And let's watch our units here. ATM cancels, liters cancels, Kelvin cancels, and this mole goes on top. So whatever my units are going to be, the only units that are left are moles, and moles are appropriate for N. And so if I do all my punchy here, what do we end up with?
Is it gonna be
I don't know if it's right.
It's a good question.
1,000.
That's what I got.
1,000 moles of N2. Okay. Good. Seems like a reasonable answer, right? (1.1 times 10 to the third moles. So what did we get? 1,087?
Yeah, but then because it's six.
Yeah, that's cool. Any questions on ideal gas law? No. All right. We're good? I want y'all to spend Eagle's Nest either working on chemistry. A lot of y'all haven't finished your chemistry that's due tonight. Okay. So finish your chemistry or work on something else.